Hello. So for those of you who don't know me, I'm Sally. I study mechanical engineering. And so my keystone project is actually my senior engineering design project, which is on metal 3D printing. Specifically, the model Concept Laser MLab Qzing R, which is a recently donated metal 3D printer to our own engineering product innovation center here at BU. And so it was donated by General Electric, and it was originally made by Concept Laser, which is a German company that soon became a GE additive recently. And we also did this in combination with GE Aviation, who actually uses this printer and other models of it in their own engines for their products. So a little overview. So the Concept Laser MLab Qzing R is a 3D metals printer, and it prints in stainless steel as well as some other materials that I'll talk about later, but mainly stainless steel for our purposes to manufacture parts. And there's a 5-step process in order to get from your design to your final finished part that you can use and sort of play with. And so the first step is your computer-aided design, which is your design, the sort of typical engineering process that you would imagine. The second step is data preparation, which is pretty much converting your design into something that is printable. So there's specific types of 3D files that the printer can actually read, and so basically converting your design into this file. And then the third step is finally printing it. And your fourth step would be unpacking. So you're not done after you've printed your part. There's a lot of post-processing that is involved that includes removing your part from the build plate that it's actually fused onto, as well as any structures that you used to support your part while it's printing. And so that's what steps 4 and 5 are for. And so the purpose of this project was, at the end of it, was to create a standard operating procedure and a submission checklist for students who want to print in the future. I say SOP, the standard operating procedure, because unlike most of the things that you would go out to buy on the consumer market, they all come with an instruction manual on how to use it. Because this printer is so, I guess, futuristic, but in the present, these materials don't exist currently. And so that was what the goal of this project was, to create those materials so this becomes more accessible to college students like all of us. So this is what the printer looks like on your left. That is this exact model of the printer that we are using. The little device on the left is actually used as part of the cleaning process after you've printed out your part. It's called a glove box, but for our purposes, we're going to focus on the machine to the right of that, which is that giant block, which is the actual 3D printer, the actual cool part. So this is located in the Engineering Product Innovation Center, as I mentioned, and that is right on Com Ave next to BU Bridge. There's a giant window, so if you want to see it, you can probably see it through that window. So why do you guys care? Why should this matter? Why is metal 3D printing even cool? Why is it cool? Well, first off, Elon Musk says it's cool, so it's got to be cool. So recently, a few years ago, SpaceX decided to use 3D metal printing in one of their newest engines in their rockets. It's called the Super Draco, and it was actually used in the Dragon V2, which was launched. And so metal 3D printing was used in this. Metal 3D printing is also used for hearing aids. A Swiss company, one of the top companies used in hearing aids and whatnot, called Sonova, actually uses metal 3D printing to create their titanium hearing aids. And in sort of a medical standpoint, BioArchitects uses metal 3D printing to create patient-specific cranial implants. And on your right, you have the International Submarine Engineering Company that created a submarine that was actually used in Antarctica. And they used metal 3D printing in their tank for that. So essentially, metal 3D printing has the capability of democratizing manufacturing. So it makes parts that are typically made in metal more accessible to everyone else. So if someone in the general population, hopefully in the future, comes up with this really cool design that they want to test out, but you can't print it out in plastic because it's not going to work that way, and you want to print it out in metal, then hopefully this will become accessible and allow you to make that prototype and sort of rapid prototype this. And so this was a quote pulled by Peter. I'm not going to say his last name because I am horrible with names and cannot pronounce that. But he is the CEO and co-founder of Shapeways, which is one of the leading 3D printing technology companies. So how does metal 3D printing work? Specifically the one that we're talking about. So it uses a process called direct metal laser sintering, shortened DMLS. I know there's a lot of acronyms. You don't have to remember them. I'll try and let you guys know what they are. But DMLS is an additive manufacturing method, which basically means you're building up instead of your typical carving out of some metal block or something. And it uses a high-powered laser in order to fuse together the cross-section of your part layer by layer. And at the end of it, you'll have your 3D printed sort of object. So you had that giant picture of our metal 3D printer, but the only part where all of this is actually happening is that tiny little build plate right there that you see over there. So giant machine, small little part. It's actually 90 millimeters by 90 millimeters and at 80 millimeter height. That is how large of a part you can print in this. So very small, which I will go into a little bit. So this is sort of a diagram of that tiny little build plate where all of this is happening. The process is a 3-compartment sort of build plate area. Your first compartment on your furthest left is actually where all your metal powder is stored. And then on your very far right, where there's a number 10, that is where excess powder is scraped into. So your middle part is actually where your part is being built. And that is where that laser beam up above is being directed to sort of fuse each cross-section of your part layer by layer, and then eventually that platform slowly goes down and layer will be added, and then by the end of it, your part will appear in that middle compartment. So compatible materials, like I mentioned, for our purposes, we were mainly using stainless steel. However, there are other materials available, especially for this printer. Some of them are steel, nickel-based alloy, and dental alloy, which is chromium copper. And there's 2 reactive materials that you can actually use, aluminum and titanium. For our purposes and safety on the college campus, we are only using with stainless steel just because it's one of the cheaper materials that we can buy, which, by the way, is not actually that cheap. It's about $100 for 1-inch cube of powder. So it is not that cheap. So when I say cheap, it's kind of relative. But if Epic actually ever decides to switch materials for students, they will have to buy it straight from GE, or because the printer has specific settings for each material, and so they'll have to buy those settings from GE. So what exactly did I do for this project other than sort of research this printer and come up with things that people already came up with? So the project objectives and goals, 4 parts: function, safety, instruction, and resources. So basically set up the printer so it's actually working, make sure all the equipment that we need for the entire process is here, make sure it's safe because metal powder when inhaled is very toxic and you can die. And so make sure all of the safety protocols are installed and known, instruction and resources so that students in the future can use this printer. And so this is sort of the process workflow from start to finish of what a student would be looking at when they're printing. Again, it's the 5-step process that I mentioned earlier. This is just a simple infographic with a summary that we created in order for students to sort of look at and distribute to them in case they ever want to look at it. So safety equipment, there are 2 types. You'll have to use these various types throughout your process depending on what you're dealing with. There's a standard and extended personal protective equipment. Standard is when you're dealing with your powder and when you're sort of doing your very superficial cleaning. Extended is when you're actually going into the machine and really cleaning it. And so extended personal protective equipment actually includes a hazmat suit. So going back to that safety issue, this metal powder, if you do sort of inhale it, you can die. So please follow the safety protocols if you guys plan on using it. I don't want to be held responsible. So a lot of words right here, but this again is just sort of infographics that we made for students to sort of know the steps of the process that they would have to take in order to submit a print and get it to actually succeed and get it to the end. So at the end of it, because this is such a new technology, we do want students to sort of review their final part and explain what went wrong, what went right, what did they do, and so that way we have that feedback. So the cool part now that we got through that, these are some test prints that my group and I actually made. These were just to test out some support structures that are available on the printer to figure out what works best with stainless steel. So that was our first draft. That's our second draft that we actually printed. And this is what it came out as. So the left side is what actually came out of the printer, and then right now it's actually fused to that build plate that I mentioned. So after this, we would actually have to remove those support structures that you see those objects laying on, as well as sort of use some sort of post-processing to remove them from that build plate. On the right there, that is not actually a print that we did. It is a print that the other group that was working on this printer as well did. And that giant block right there was actually the BU rocket team, not us. They used the printer without knowing any of the instructions that we researched. So as you can see, if you don't have this information, that is what happens. You get a giant brick that has a lot of holes because it malfunctioned. But that is what it is. I also created a bottle opener because when you're a college student and you're working with a cool machine, obviously the first thing that you want to do is create a bottle opener. And so if any of you guys want a closer look of what an actual metal 3D printed object looks like, feel free to find me afterwards and I'll show you it. But that is pretty much the end. And before I conclude this and take some questions, I want to thank a couple of people. I want to thank Concept Laser and GE Aviation for sort of supporting us and donating that printer, to the staff at Epic and my faculty advisor, Professor Anna Thornton, and my group for making all this possible. And I would especially like to thank Anna Kels-Nelson and Rick Tonetti and the Coalition Symposium Committee for sort of supporting me through this entire thing, because this semester was really stressful to get all of this up and down, like working. So thank you to you guys and all of you for listening to my PowerPoint. So, any questions?
Well, what's the resolution on this machine? Because there's pretty small parts. How fine does it get down?
Yeah, so I don't have an exact spec for you. I would have to pull that from one of our documents, but it's actually very close to spec, I think within 0.5 millimeter. Yeah.
So the BURPG team made that
Giant block, yes.
Did they at least remember?
Not throwing shade, but.
No.
Did they at least remember the safety procedures?
I don't know because I wasn't there when they printed it. I really hope they did. I mean, they're still alive and walking, and I haven't been sued yet, so I'm assuming they did to some extent. Yes.
So you mentioned there was a quote from the Shapeways CEO that metal 3D printing is the future.
Yes.
Do we think that this is going to become much more affordable than like a personal CNC kind of setup for people?
Yes. So there are some companies right now, some startups, it's actually one in Cambridge right now called Desktop Metals, that is working on sort of making this a more one-step process rather than 5-step process, and also making it more safe without the hazmat suit. But that probably won't happen until, I want to say, like 10, 20 years. So it's pretty far off. I think right now, for the purposes of what is available on the market, it's probably best suited for a manufacturing line rather than the consumer market currently.
Support structures for the prints, are those like generated, or like how did you design them? Are they generated via like the SolidWorks or like the interface where you go to print it?
All of the above. So you have a couple of different ways of doing it. There's a software that you can use that will help you generate it. That is probably the easiest way. And then you can also make your own from SolidWorks, just designing it into your part, which is a little more difficult. You kind of have to play around with it, which is why we were playing around with it. So that way, possibly other people can just be like, oh, just design this and it'll work. But yeah, so there's a variety of ways you can design those supports. Yes.
Is there any difference in the strength of the metal with it coming together as a powder versus something being whittled down from a...
So currently, with this printer, if you actually do the correct post-processing, which includes heat treatment and annealing of the part, you'll reach 100% of that same strength. Because BU does not currently have the annealing oven available on hand, you can probably reach around, I want to say, 80 to 95% of the strength that you would normally achieve. Yeah. Any other questions? All right. So thank you.